All right, so yeah, we got a lot of full slides today. So I'm going to try to go through most of them fast, and the ones that I think have the more intricate details, we'll cover a little more in depth. So I'm going to introduce those of us who might not be super familiar, need a little refresher, a little bit about steganography, and kind of eventually get to this point where we're applying some old techniques to new technologies. And that's basically what this project I've been working on, essentially coming up with a file system that operates within other data. And we'll kind of take it to the next level and consider the ramifications of doing something like this, as well as, what if somebody's already doing it. So just to kind of get things going, Stego might be something as simple as somebody posts a classified ad, says, hey, wanted single white female, whatever, right? That's all entirely code that really means something else. Or it might be something more subtle, something that's part of another message. Say you've got inside the little tiny period of a letter, on a printed letter, you've got a bunch of little tiny ones and zeros that are real subtle to the human eye, but if you know what you're looking for, you can decode those and there's your message. So the more interesting, at least from where I'm coming from, ways to implement Stego would be using something you might be a little more familiar with, like taking an image or some other content and finding some either unused space in that media, something that might be reserved for comments or metadata, something about the data, instead of the actual content itself. Or maybe you can tweak it a little bit so that the original content is still represented. It still describes the original thing it was doing, but yet you've tweaked it enough that it actually has another subtle meaning. So usually most people, when they think of Stego, think of it that way. They think of, okay, we've taken the least significant bit, the little tiny piece of information that doesn't make as much of a difference as the rest of that, say, talk about an image, a pixel, the very, very least significant bit that represents that pixel color. And we're going to do things a lot differently than that, but it's important to understand that that somehow you can have data that isn't as important as the other data, and then that's what we can leverage to either hide more data in, such as a serial number, watermarking, or actually exceed our normal storage capacity. It is kind of the way I like to think of it. So, like I was describing the classical digital steganography, steganography, you can do that a couple of different ways. I like to think of it, even though there's much more clever and interesting ways to do it, but say you've got some number representing the color, or say it's an audio sample, its numbers representing the magnitude of that audio sample. If you just round off that number, an even number when you're going through the media could be a 0 and an odd could be a 1. Real simple. You don't have to think about real complicated encodings here. So that's kind of what I'm basing the rest of this talk on, is this very simple description of steganography. Yes, you can get much more complicated. You can get much more clever. You can use other techniques to compress more data into the data you've got. This particular project I've been considering actually for a couple of years now. The growth of what's unfortunately called the Web 2.0 new media environment. Sites let you upload videos, prime target. You can cram a lot of data in a video file. They take a lot of data. And we can also leverage that. I also started considering the ramifications of what we consider a viral marketing. Somebody downloads a video and forwards it around. Well, wouldn't that be great if I wanted to have my data mirrored by not innocent bystanders, I shouldn't say, but by the random public. Sure, you can maintain my backups for me. As well as the actual marketing aspect of it, where privacy concerns. Okay, what if somebody's already tracking these videos with some sort of watermarking under the hood, and people are forwarding around? What kind of, one, how would you do it, and then two, what kind of issues come into play because of it? One of the issues considering this kind of a mechanism, say you take a video, upload it to, pick on YouTube today, youtube.com, you upload it, it will convert it. It just does. It resamples things, compresses the audio, and does other things. And if you just have your secret code encoded with just something simple like that least significant bit mechanism I mentioned, your code will actually be destroyed mostly because of the compression and the tweaking and the changing that they do to the video. So that's probably the biggest issue we have today that I'm going to address, is how do you make that stenographically encoded data survive one, maybe even two or three or four conversions between different things. We can do it a couple of ways. We can try to pick something that when we upload to the system that's hosting it anyway, that it's not going to do as much conversion. Okay, it's not going to tamper with the bits too much. If we can pick that from the get-go, we'll be doing pretty well as if we include enough redundancy of our message in the host media itself, we'll be in pretty good shape. So this is the kind of thing we start thinking about when we talk about distributing the Stego. Keep in mind, too, though, that there are other ways to encode data. I like to use the misspelling of the blog comments, right? If you spell a the with a TEH, that could represent a 1, and for all the zeros, just that regular English text, or whatever language you want to pick, the regular spelling could represent a 0. So at the human eye, that doesn't look like a message is encoded. But if you've expected that, you can now decode the message. Of course, the conversion here would be if there's an online, you're submitting it via an online form and it does a spell check for you, would be an issue. Or, for example, using double spaces instead of single spaces. Your browser renders HTML. If it's not a non-breaking space, it will just collapse those white spaces into one. And at human eye, it doesn't matter. You download it, though, and now you can see that there's extra bytes there. So we can use these in combination, maybe even alternate between the classic media, image, audio, video encoded messages. Or maybe we just use consider this an out-of-band type encoding to represent maybe the structure that we're storing the actual data in. This is how we can find the data we're looking for. Of course, it's pretty hard to prevent and to police all the blog comments, right? So it's going to, more than likely than not be tampered with. Talking about the upload, the conversion is usually not going to be as damaging. So it's a good candidate for our structure for such a file system. So to kind of throw a few ideas out there, StegoFS as it's still, I guess I should call it pre-alpha. It's still, well, I wouldn't want to hand it out, which is why I don't have a link to download it yet, because I still have a lot of work to do on it. But it does do a few things. It does use URLs, and the first version had a dually linked list. So it would actually have a URL that pointed to this block, a URL that pointed to the previous block, a URL that pointed to the next block. And that way, if you were navigating through, you could find, okay, yet more data, and now you could tie everything together. So your URL could be a blog comment, and then the next one could be maybe a video or whatever. Originally, that's how we were doing it. But for the example I'm going to show here, I'm actually going to use a flash video on YouTube that I actually picked one that was already up there that I anticipate nobody will see. So there's less funny business going on. And I go ahead and I encode 1 bit per pixel and store some extra bits to make sure and check that those bits haven't been converted. Generally, what I'm talking about here is what we call forward error correction, right? So there's been, especially in the last couple of weeks, there's been some interesting news articles, a little bit of press coverage about forward error correction. There was a thing a few days ago. It was either Dig or Slashdot. They're talking about the Viterbi Engineering School. Viterbi, named after the guy who came up with a lot of the forward error correction. We use this stuff in data communications all the time. It's not new. The one I'm actually going to use, I'll show in a minute, is actually a Hamming code based off of Dr. Richard Hamming work. So, because I think that's the easiest one to understand. My point is, though, we're going to try to prevent, if we lose 1 or 2 pixels, 1 or 2 bits, because they've resampled the video or they've stamped a watermark of their own over the top of it, we can still fill in the gaps. We can also extend this across things. So consider I might have multiple frames of video, for example. I could have it mirrored, repeated through multiple frames. Now, if one of those, maybe my error correction isn't good enough on one frame, if I average it with the next frame, I might be able to figure out what it was supposed to be. So if you want to look up some more information and it's late in the afternoon, your eyes are rolling in the back of your head or whatever, here's where I suggest looking most. To go to Wikipedia's entries for Hamming code is really good, and look up some of these other terms. These techniques are being revisited quite a bit now because of the progression in quantum cryptography, quantum computing, and other things. So it's a hot topic. Now I'm using a Stego in media example, but the error correction techniques are definitely alive and well today. So for our Hamming code, I'm going to encode 1 byte. Okay, it's going to be hexadecimal FF. And for this example here, the underlines that I have in this first bullet point, each underline is going to be a parity bit. The first one, the very first 0th position, is going to check every other bit, including itself, actually. Starting counting with itself, and check every other bit. And this is going to be an even Hamming code. So we're going to want to have an even number. All right? So if we take FF, right, that's 8 ones, essentially, in binary. So to figure out what our first check bit should be, we look at every other bit. So of course, we'll come back to ourself later. We skip a bit. The next bit is a 1. The very first bit of the data that we're actually storing is a 1. So we've got 1 so far. We skip another one, which happens to be a blank so far. The next bit, we've got a 1, and so on. We actually end up with 5 ones. And that's odd, but yet we're doing even parity, so we need it to make it even. So we actually place a 1 in our check bit state. Now, if any one of those bits has been flipped to a 0, we can now detect that. But the key to this forward error correction is actually in the layering of the different check bits. Okay, take the second one, for example. If we check, the second bit's going to check 2 and 3, 6, 7, 10, and 11. So the same thing applies. We add it up. We happen to get another 5 ones. So now we store another 1. And I'm not going to go through everything else on the slide, but the point is we've got this pattern, and how do we actually detect and correct when something's wrong? Real simply, if we go through and add up the bits that lie, okay? If we go through and check and say that the bit 2 that's supposed to check these other ones doesn't add up, and the 8th location also doesn't add up. We add those together. Well, it happens to be that bit 10 now is the one that was damaged. And that's just the very simplest way I can describe to you forward error correction. We're using 12 bits to describe 8 bits, and 12 total bits to describe 8 bits of data. And that can let us detect a couple of mistakes and always correct at least one. Now we can add and keep going. There's extra tricks, make it more complicated to correct more than that many bits. But now if one of these pixels has been tweaked in our stegoed image frame from the stegoed video, we might be able to correct it. Now notice I didn't add 12 bits to the image. I'm just rounding off choice ones I want to. One thing I like to consider too when doing this is how to extend it from other materials. See, we have a history of really poor, actually, steganographic techniques. A lot of them are pretty bad. If you just Google and try to find a stego tool, it's probably not going to be very good unless you pick something really clever. There's easy ways to detect a lot of these tools, detect what appears to be a use of the tool, let's say, by doing things like looking for near duplicate colors. If we've tweaked just that little 1 and 0 throughout the whole image, then there's going to be a lot of colors that are almost the same, but not quite. And yes, I'm overgeneralizing, but you get the idea. It's easy to detect. And then because we're putting in a pattern that changes the pattern that's already there, the compression capacity changes of the content, the host media we're looking at. So, of course, we can just go real low key and only encode in very select places. And it'll be a lot less likely to not just be detected, but it's going to be a lot less likely to be damaged in a lot of ways. If you're not replacing everything and just replacing some things, especially on real quiet frames, like there's not a whole lot of color in that frame, you're going to want to be more subtle, so it's less likely to, like I said, get detected, but also to be damaged when the things start getting compressed. And the online engine, as we're doing it in this example, goes through and tries to make colors, oh, this is a close gray to that gray, so let's make it the same gray, and so the video takes up less space, right? That's kind of the way it works. If we encode very sparsely, we're not going to have that damage happen in that way. So again, remember, we can store things in the data itself. We can store data about our data. And we can store things, well, let's say, what could we store? We could store something like a serial number. By using Stego, we can now say, hey, I uploaded this video to YouTube. If I want to find out when somebody tracks it, someone's downloaded it, where they got it from, I can now look at their copy, compare it to the one I encoded, and I know which one they had. But the other thing I want to kind of expand on is, what if we use a visual watermark to hide our data in? That is, you know how you go to YouTube, right, or whatever, MySpace, whatever you do, there's the YouTube logo in the bottom of the video. Well, what if we make a YouTube looking like image to hide our Stego in? See, when you use something like YouTube, most of these things will do a matte layer in the player that doesn't actually encode in the original media stream, so that if you actually were just to download it, there's no logo and there's no watermark from YouTube there. But so if you're viewing it, YouTube's logo's over the top of your Stegoed one. But when you download it, there it is. So some techniques like that. And actually, what I'm going to demonstrate is just like kind of like a barcode, a watermark. This was an interesting topic to try and prepare for, because how do I show you something that's designed to hide? It was a real hard one to think up. So we'll get there shortly, though. Excuse me. All right, so mostly what I've been covering so far is making one frame survive conversion. That is, one image, one point in time, survive that. Take, for example, say you've got a video you're uploading that's at 30 frames per second, and the engine you're uploading to decides to, hey, let's take it down to 15 frames per second. Well, that's going to chop out every other frame that you have. And if there's not if the ratio between the 2 frames per second is not evenly divisible, now you're going to have a problem where there may even be new artifacts created when they take 2 frames and average them together. So to make our encoding survive the resampling, we're going to want to mirror between the frames the encoding that we're using. Okay? So we can survive drop frames, and we can survive that extra bit of information that sometimes is added when people resample at a non-divisible rate. So just to kind of illustrate that, why don't I just pull up the... Here is a video I uploaded to YouTube last week. I have up here in the upper left the watermark. Now, I know you can't see that, so I have a magnifier I'm going to bring as I start playing this. All right, this is the upper left corner here of the video as it's playing. This is the same FF encoding that I showed you with the Hamming code. We have actually 3 semi-transparent bits, and then we have a black bit, which is going to represent that 0, and then continuing on the pattern. But I've actually done it 3 times in a row. As the video is playing, we can average those frames ourselves and figure out, okay, what is the most unique? You know, okay, this is gray most of the time. See, right now it was pretty damaged there at that second. But I can take this, do 3 different independent samples across the whole video, and I can figure out what is most likely to be the ones and zeros. And now I've basically survived this FF encoding across everything. All right, so that's kind of the idea. Now I've just done this in the black area, so it's a little easier to see, and I use the 50% transparent with white. But you can use and choose the colors very well and hide it in a more appropriate part that's part of the image and not up in an easy to find place. Okay, that's just for demonstrative purposes. So that's what the StegoFS tool encoded the byte FF with. All right. All right, so we're talking about that. Now, it's not super obvious, although if you know what you're looking for, you could see a lot of that. You might, do some other interesting things. One of the things I was contemplating doing, I wish I had more time to do this, but, use the, the old-time reel-to-reel type film that would show the patterns, the streaks in the film. Use those and actually have them represent a barcode as the video is going by. You can do all sorts of techniques like that to store this. You don't have to have it as blatantly obvious as a demo. I just had to try to make it so pretty much everybody could see it for today. So you can also add parity across the frames. I just talked about mirroring the frames so far, but you could parity the frames themselves in either a Hamming code in yet another dimension across the frames as a different way. Take, for example, here we've got the 2 bytes encoded. Just an XOR example. Not real creative, nothing new, just something we're doing in a different way that I haven't really seen anybody do before in this dimension. So I still have to rewrite a lot because I haven't used the actual libraries. What I had so far was just command line scripts glued together. So between ImageMagick and FFmpeg, here's what you could do to replicate exactly what we did here. We're going to run the convert command to create. This is the code, the gray, because it was 50% transparent, white and black, and using black fill points. And here these points are the zeros in the first command line option here, the first line, to create an intermediate image. Now this is the watermark image we will actually use. And then what I do is I create a third image, I create another image that has it 3 times. And then I go ahead and make sure I've enforced the transparency and create my actual watermark, that FFmpeg, with the video hook library, which is getting rewritten. It'll be interesting to see the newer version that comes out after Google Summer of Code. But in this way, and actually this particular one I ran on Windows with FFmpeg and not on anything else. So it works quite well to create the coded MPEG. And this is at that point, we upload it. To read it, of course, you've downloaded it, and I'm not going to bother showing you scripts to download, but downloads it, strips out everything, saves it as individual PNG files, goes through and peels off where we've placed that watermark, which, again, I think the more interesting use would be to make it look like the YouTube logo or something that would be hidden, overlaid with the matte version of the YouTube logo. And then we can go through and do our averaging, do our parity checks, and whatever. I didn't have enough space to show you everything on the slide, of course. So this is basically what StegoFS in its current state does inside of a Fuse module. Fuse being the file system for userland. So to kind of reiterate, we have that frame as an image. We've peeled that off. Okay, if in that particular frame it's damaged, we can try to repair it inside the frame or try to repair it by referencing the next frame or the previous frame. Okay, or some other out-of-band encoding, right? We still have the audio we haven't been playing with. We might have other things we've stored somewhere else. Maybe we've mirrored the entire video somewhere else with a different provider. We've uploaded one to YouTube, one to MySpace, let's say. Okay. We can prevent detection or, well, at least make it a little less obvious if we don't just obviously choose those colors in that spot. We can also extend it to many other excuse me, many other ways. Another aspect of this is I don't have to just store the URLs, right? I could ask Google to find them for me, or I could make it a little more dynamic in another way, trying to extend the concept we've gotten. There's some other interesting things we can do. By the way, I've already got a link to this presentation. The one on the disk for the con is not complete. There's been a lot of changes since then, so you'll probably want to download. I've already got it up here if you want to download the full PowerPoint already at bluenotch.com/resources. We have, though, to consider, all right, so you can hide stuff inside of videos. Yeah. What's new? Well, we're trying to do it in a way that's easily accessible inside of a file system format. Now, you might not be interactively, editing a file well, it's not going to be practical to edit a file, right? You're going to have maybe multiple videos. It's going to have to download. If you edit it and make it right, it's got to upload. You've got to wait 5 to 20 minutes, depending upon the provider, for them to compress, re-encode it, make it available, and so you even know where it is so that you can reference it in the file system. So it's not something you interact with like a normal file system, but we use the file system as a mechanism to store inside of there. And then now StegoFS could do all that stuff we need to do for us. Extending it, though, what else could we do? Well, video uses keyframes. Basically, when you're skipping ahead in the video with the progress bar, whatever you want to call it, the way that you can do that is because they've keyed in frames that kind of show approximately where in the video it is. They're not really content. Sometimes you could, if you wanted to, make a video with no keyframes. I think you might have to have one to start with. I'd have to read the standards, but to see if you can even start with one without any. But you could use, say, one keyframe. If the next keyframe is with less than 5 seconds, that's a 0. If the next keyframe is over 10 seconds, that's a 1. Now, you're not going to store a whole lot of data there, but you haven't manipulated the video at all. All you've done is you've changed the way people can seek in the video. And of course, there's other things. There's metadata inside the video. The MPEG standards allow you to put in some comments, and there's other things you can do to hide data. But I think the one I'm probably going to try next is to make a watermark of my own, look like another company's watermark, so that when their watermark's overlaying mine, you're not going to see my watermark. But when you actually download it and view it, you see mine, which you think is theirs. So I think that's probably the way I'll have the next demonstration go. The other thing to consider, too, is it's not just in immediate content. We can have anything we can signal and reread, we can store something in. Just like think of dynamic RAM. Every time you read RAM, you have to rewrite to it, DRAM. Well, what if we had something like a spoofed DNS request, and then when the reply comes back, or it resolves to our DNS server, that represents a 0 or a 1. Now, I'm not talking about tunneling or using DNS as a covert channel, as you probably have heard of it before, which is a great technique, but I'm still thinking along the timing realm, right? I can spoof a DNS thing, see the result, or shoot, don't spoof it, just do it. If the result comes back in less than 5 seconds or more than 10 seconds, again, now those could be 0s and 1s all day long. Now, that's a lot of overhead for encoding 1s and 0s, but you're not actually storing anything anywhere. The problem you would have is you'd have to constantly refresh that data, right? You'd constantly have to resend the DNS traffic to keep that media alive. But now on the wire, you've got a file system that's never actually stored anywhere. So that's kind of one of the things I hope to add into StegoFS before I release it is some of that. It's still very pre-alpha quality. It's especially with the video sites. It changes so often that it's really difficult to squeeze the most out of it. Actually, last week, the demo I showed you with YouTube video never once showed any kind of variation. It always was the same. I thought that would be a very interesting demonstration. It looks like I just hard-coded that on every frame. But anyway, it's a moving target. So I hope to add in some of these extra features. But you get the idea. We can still extend this into other forms. Anything we can store more stuff in, is what I'm saying. Now, as I started to work through some of this material, I stopped to think about, other companies' watermarks. And I thought about, well, what if they're already doing this? It's pretty easy to encode and watermark and serialize things, and I know people who do forensic investigations. I do too, but I mean, some of the people I know of that have encountered and have been investigating people who have had material that's been serialized in a steganographic type way. But what about the viral marketing aspect of people trading around things? Now, maybe using something, maybe not a full file system version, but they're still storing those blocks in. They're using it redundant blocks, redundant bits. Not so much, now they're doing that. Yeah, we probably were paranoid about that already. But what I found is I can tell how they got it. That is, if you download something from YouTube, I can tell if my number was that pattern I showed you. It looks different when it comes from YouTube than from MySpace. So I can tell you where you got it from. I can also, if I make it robust enough, my pattern, I've been playing with it a little more, I can tell that you download it from YouTube first and then re-uploaded it to MySpace and then record it to an AVI file. I'm trying to see how far I can take this before it gets crazy, but that started to kind of freak me out a little bit. And the more I work with it, the more I find I've overcomplicated the problem. It's so unbelievably easy to do that. So, there's some large privacy concerns here. So basically, I just tried to apply some old techniques to what we, unfortunately call new media. Considering the impact of some of the problems we deal with today, that is, we're running out of space in a lot of ways. I mean, as a security professional type person, I can never keep enough tracking information. And sometimes those relationships are what I'm really concerned with, not the actual serial number. I just want to know how you got it, right? So kind of like, like what the Paterva guys did with Maltego, right? The relationships is the data. That's what we really want, not so much the data itself. Yeah, it's important, but sometimes the relationship's more important. So I'm, in considering this aspect that we can use those relationships. For example, I talked about the relationship with respect to time, with the keyframes and the DNS traffic, to encode those ones and zeros. So even though we're physically only got so much space in storage to store something, we can actually store more than we can have physically stored on the device itself that way, if we pick the relationships appropriately. So, and that's not a foreign concept either. The relationships between hashes and rainbow tables and the chains and everything that goes on there. I'm not going to get into that. But essentially, what I'm talking about is creating a reduction function of the data and the relationship itself with steganographic techniques. So it's easy to consider how you might be able to extend this to other current problems, like some of the issues we have. Quantum computing, if somebody reads something, they've tampered with the data, right? It changes when they read it. Forward error correction, very important. I have a few things. I'm going to eventually put up a link on bluenotch.com/resources where you can download the Python module once I try to add in some more things. But I do have a copy of the presentation there that's current. If you want to look at some of the Flash video source, originally I wrote it in Perl for the older FLV codec standards, but since YouTube moved to MP4, I thought that was kind of starting off on the wrong foot, so I just dropped it all, started off getting more in depth with Python as the framework I'm using, and using MP4 as my tests. But these techniques, of course, apply to other ones. If you want to look up the Hamming code, probably the easiest place to start is this Wikipedia article. And I did run across somebody else doing something a little similar. There's a virtual dub filter, which you can look at on this URL. I could never get it to work, but it's an interesting concept. They show a good demonstration of hiding a message and then adding the redundancy that would survive converting from an AVI into another format. So it's basically a different way of explaining some of the things I've explained today. That's pretty much all I had. Q&A in 104, right? So go over there for questions, unless you want me to play the rest of the Hacker Videos trailer. No? Yeah? All right. I don't know if the sound works very well in here, but why not? Just for fun. Thanks, guys.
Beneath the world we know
Hard drive space, sorry.
is the world they inhabit.
Hey,
Yeah.
what you doing?
I don't know if you can, maybe you can see it a little better now in full screen. You see the watermark I've got up in the upper left? Yeah, so, all right. I'll let it play, I guess. Maybe that'll make everybody clear out the room if I play the Hackers trailer. All right. Yeah, I tried to find something no one else would be viewing so that when I was doing my test, I could tell if I was the only one going and fetching these files. So obviously no one ever watched this besides me. So
I'm taking over a TV network.
I finished up things.
Hackers penetrate and ravage private.
all right, I'm not going to play anymore. My hard drive's pegged for some reason. So all right, that's all I got. Thanks. I'll see you in 104.